Good morning, everyone. Welcome to day 3. If you've made it this far, congratulations. That's no small feat. Couple things before we get started. First, we'd really like to give a heartfelt thanks to Janus, Roy, and Ryan from our outreach team on coordinating this heroic effort. So thank you everyone for that. The second topic we just want to discuss real quick, and we will be talking about this throughout the day, is we would like to continue these conversations. This is not something that we'll just do once in a vacuum. So we would like to encourage all of you to consider perhaps hosting the next event. Perhaps we can all be green ambassadors and meet in 2021. So just food for thought. So I am going to present for the first 10 minutes, and then I'm going to hand it off to my colleague, Lucas Joppa, our Chief Environmental Scientist, to talk about AI for Earth, and then we will collectively be taking questions before the end of 9:30. So with that, I will go ahead and get started. So my name is Asta Roseway. I'm a Principal Research Designer with the Urban Innovation Initiative at Microsoft Research. I'm here today to talk about future scenarios. And as Scott mentioned, we are an interdisciplinary team. We cross design, electrical engineering, software, and machine learning together to kind of infer the next wave of sensing experiences around the environment. And so I want to get into the first topic, which is our mini ecobits. As Gavin mentioned yesterday, ecobits is kind of our next wave of sensing experiences that we will be exploring later this summer. Our intern, Alex Cabral, will be sharing some of her work in that space. But this really is kind of, as Edmund mentioned yesterday, it affords us the ability to enable people to act as sensors walking around the environment. And, you know, we are looking into ways that we can gamify the data that we collect, engage kids K through 12, perhaps even open APIs. And so this is kind of where we're at and where we're starting. But all of that doesn't mean anything if there's nowhere to go with it. And so this is the idea of having sort of an eco pop-up lab. This is something that we've been discussing in our community outreach group, more specifically. But the idea is like, give people a place to go. Give them a target, an area that they can converse with the scientists. There can be champions in the local neighborhoods that get educated and can convey what the sensors are doing in the environment. And this affords people to be able to volunteer, have lecture series, and even engage in local art communities. So this is a topic that we will be diving into deeper today in our discussions, but we think that there's a lot of potential with these notions of pop-up labs. Other things we've been thinking about is ways that we can augment existing services. Let's take two examples. One is you have a very sort of transitory service such as Lime bikes or scooters, and then the other you have a more stationary such as Starbucks. So imagine being able to augment these things to actually collect data for the environment. So imagine if you augmented 6 million scooters worldwide to collect particulate matter and being able to overlay that on top of the Lime bike experience. You're just leveraging something that already exists. And same with Starbucks. Imagine if every Starbucks in the world had a stationary sensor on the outside of its store, right? So these are things we're just kind of seeding your minds to think about, because there's no reason that we have to start from scratch. We can partner with these entities and leverage their existence. So we all know that we're living the mobile life. We've been living it for quite some time. I think the Alan Turing Institute was sort of inferring the notion of helping people navigate around sort of polluted streets. And so we've taken the concept of Waze and turned it into haze. And you can imagine being a jogger and running down the street, and all of a sudden there's like this cloud kind of coming up in front of you, and it routes you to, you know, a safer place to run, right? It's a little bit high level, a little bit whimsical, but, you know, I think for just common folks that aren't necessarily scientifically minded, this could be a great way to sort of bridge them into the next wave of being aware of their environment. Also, for all you Pokemon Go fans, imagine being able to collect, you know, little characters like little, you know, noxious gases and particulate clouds. This is another way that we can also engage the young generations to learn and understand science through the gamification of environmental sensing. And we all know that augmented reality is very much on the horizon. It's coming. So I can't help but to think of Ron Cohn's work at UC Berkeley, and being able to leverage the idea of using your screen as the next sort of almost like a sixth sense, if you will, just being able to wave it around and see the gases that are going by, because ultimately people don't understand what they don't see. And unfortunately, it means that things have to get really severe, like smoke or smelling sulfur, for people to understand that something's going on. So how do we leverage these technologies to raise that kind of awareness? And one of the things that we do at Microsoft is we really believe in inclusive design. We really believe that everybody should be a part of this experience. And we've been sort of in early prototype phase of translating air quality into sound. So whether we're using major or minor chords to infer a shift in air, or perhaps, you know, a certain sort of chords. But imagine, you know, if you have these sensors everywhere in your neighborhood and you have your AirPods on and you're running around, you can actually hear the air getting better or worse, depending on the granularity of the data that we can provide. But imagine being able to sort of echolocate, you know, where you are in space. Another thing I want to mention is, you know, art has the ability to transcend the mundane, and I co-run the Artist in Residence at Microsoft Research, and this is an instance of how we take collective data in our building and we infuse it into art. And this is Ada, which is our AI and architecture piece, and this notion of materializing data is something that art and artists can really do in spades, and here's an example of that. In 2015, this artist created the experience of being under 10 feet of water, which infers like what will happen when the polar ice caps melt. He used lasers and smoke to actually create an instance of the water levels in Amsterdam that would happen, you know, maybe 20 years, 50 years in the future. And it has profound effect. It has ways of moving people from just data overload to sort of more visceral and emotional responses. These kind of experiences move the heart and they move people to action. Other things we've explored is also through our Artist in Residence is the idea of interspecies communication. You know, being able to have a conversation with a plant, a house plant, can actually really change people's perceptions of, you know, the value of what plants, environments, and trees can bring to our lives. And Project Florence enables people to say something via text. We translate their text by using a NLP algorithm, and we infer their sentiment, and their sentiment becomes a light frequency that hits the plant. The plant then has a response to that light frequency in addition to the other sensors we have in it. So the plant has a mood, you have a mood, and then it prints out a response. And it's whimsical, and yet you can actually break these down into educational tools. Here we've explored the ways that we can have a grow kit for kids, and they can build their own interactive Florences. So there's no reason why we can't, you know, sort of start pushing into these spectrums of next generation curriculum. Now I'm going to totally pivot. I'm going to really pivot hard. I'm going to talk about next generation sensing. So at Microsoft Research, you know, we have the affordance and the opportunity to explore futures 5-10 years out. And one of the things we've been exploring is ways that we can go beyond the digital device, go beyond batteries and components, and leverage the natural world to actually start inferring things around us. So here we're using colorimetric chemistry to actually change pigment color to let you know what you're being exposed to and by how much. So you can imagine it integrating into pigments, whether things that we use paints on our houses or things on our clothing or our person. And we've actually explored this. So this is Eco Patches, recently published. This work it uses colorimetric UV dyes that users can actually print out with their inkjet printers. And we augment that with computer vision to do an analysis of the color changes. So we allow people to see the color change with their naked eye, but also do an assessment with computer vision that enables it to be captured in time and plotted on a map. And we've gone even so far as to explore what happens when your hair color changes. It's not that crazy to think that maybe 10 years from now, the very things that we put on our bodies, whether it's lotions or hair color, can actually serve to tell us what's happening in our environment. So this is UV index hair color that actually changes in brightness and saturation when you go out into the sun. And the higher the UV index is, the brighter your hair color. It's actually kind of amazing to see it in real life. And so this is where I'm going to stop. I'm going to just express that there is a big gap between people's understanding of what's going on in their environment. And the notion is if we can create these very hyper local experiences where you can really see what's you've been exposed to, perhaps we can bridge it to the collective. So with that, I am going to hand it over to Lucas, and thank you so much for your time. Looking forward to your questions.
All right, thank you so much. And thanks everybody for coming today. My name is Lucas Joppa. I'm the Chief Environmental Officer at Microsoft. I actually started my career inside Microsoft Research. So I had the privilege of working on environmental topics inside one of the world's foremost computer science laboratories. And so have really built my career and Microsoft's work at the intersection of environmental and computer science. And I've had the privilege of collaborating with Asta and her team for many years. I've always been extremely impressed with what they're doing, particularly some of the on-body sensing work, although I think the hair color changing for me is probably a non-starter. But other than that, I'll take the sensing tattoos. And what I wanted to talk about really quickly is just some of our perspectives and ways that we're working on shaping urban development towards a more sustainable future, and particularly to think about how we're doing that through a specific program that we designed called AI for Earth. And AI for Earth is Microsoft's first initiative in what's kind of been more generally known now as the AI for Good space. It is a program that is specifically dedicated to deploying our over 35 years of research and engineering and machine learning and artificial intelligence in the 4 key areas of agriculture, water, biodiversity, and climate change. And we've built that program up. It was kind of an idea that started in Microsoft Research actually a few years ago. To about 2.5 years ago, it became a 5-year, $50 million investment on behalf of the company and a template towards many of our other AI4 programs like AI for Accessibility, AI for Humanitarian Action, and AI for Health. And in the time that we've been in operation, we've really scaled the program for the total number of organizations that we support. And we support institutions and organizations through simply providing access to cloud and AI technologies through grants. We believe that organizations that are working at the intersection of machine learning and environmental sustainability budget shouldn't be a barrier to them making progress. Recognition that, the world's kind of sustainability experts and environmental scientists aren't necessarily the world's experts in computer science, and building education programs to close the gap the skills gap between those two fields, and then working hand in hand with a few organizations to really build out new applications. And we've built that program up now to supporting more than 620 organizations across 90 countries in the world. And that geographic diversity really matters to me, and I think it probably matters to everybody on this call, because we all understand that climate change and its impacts manifest themselves very differently in space and time. And so being able to work with partners in all of these different places that are experiencing different impacts differently is extremely important to us. And one of those areas that we work is in urban settings, and I'll talk about that in just a little bit and some of the unique challenges that we are looking at in that area. But just really quickly, what AI for Earth is as a program is it's an attempt to scale ecological insights and environmental insights through the deployment of technology, really focusing on providing the infrastructure, the data sets, the machine learning models, and then going beyond that and making that model result available through scalable technologies like application programming interfaces or APIs that can then be ultimately ingested in end user specific applications. And I'll show you an example or two here in a minute. And to do that in a way that really brings together the data and model and infrastructure contributors with the consumers, and to start to build that online ecosystem of a new way to monitor, model, and then ultimately manage Earth's natural resources in urban and rural environments. And really, when we think about that, there's 4 key application areas that we're really investing in as part of our broader work inside AI for Earth and the planetary computing platform that we're looking to build over the coming years. And that's really these 4 areas of classification or quantification, this understanding of what is where and how much is there. An idea or a work stream around forecasting, being able to predict what will be there. An idea around planning, so for us to be able to say what should be there. And then this idea of attribution, something that's so important to anybody that's actually working in this space or funding it, to understand the answer to the question of, is the outcome or was the outcome dependent on my intervention or not? Because if so, fantastic, we can study what worked and what didn't. If not, then we need to figure out why I didn't have any impact. And there's a few examples, I think, of grantees where all of that AI for Earth works with, where all of this really kind of comes together in a nice way. And Breeze Technologies is a really interesting one. And Breeze Technologies is really focusing on air pollution and air pollution globally. And the way that they're doing that, and the reason that they're doing that is for all the reasons that everybody on this call is probably well familiar with. Air pollution is a dominant cause of mortality for over 7 million people in the world, causes economic damages over $5 trillion every year. It's one of the most pressing, immediate, near-term environmental challenges that we have to address. And so what Breeze Technology is trying to do is to scale this system of over 10,000 air quality stations that are on the ground in regions around the world, and in collaboration with the European Space Agency and all of the remote sensing data that the ESA has and Microsoft's AI for Earth program, to build machine learning models that can take what we know from those 10,000 air quality stations, scale it by combining it with that satellite remote sensing, and turn that into millions of data sets per sensor that we're able to deploy around the world for 13 different air quality indicators, and put that in the hands of urban environmental management professionals to get out ahead, well, both to understand the state of air pollution in the regions and cities within which they're operating, and to get out ahead from public communications and public action perspective. HighTide Intelligence is a fantastic one, I think. Started by a group of Stanford students really looking at the issue that many different urban communities are situated in regions, coastal regions that will be significantly impacted by changing climates and rising sea levels. And the idea that those communities, especially across economic and economic distribution, will be impacted significantly differently, and being able to get a very high resolution estimate of climate models, sea level rise, and then economic damage to a particular property is the level of resolution that we're going to need to get to if we're going to be able to really bake this in and get specific home and property owners to properly account for and realize the risks that their properties may represent. And so they're starting in California, in certain counties in California, and then looking to scale to more urban areas around the world. And then the last one I just wanted to talk about really quickly is a project underway with World Resources Institute in collaboration with AI for Earth. And it's really this key issue that urban areas face in the hot summer months around urban heat islands, and the significant increase in mortality that happens, particularly amongst our elderly population or folks with health, pre-existing health conditions, that our urban areas, as we know, just absorb heat and just become this kind of this specific little furnace on the planet's surface. But we also know that we could improve or reduce the heat island effect by adding reflective surfaces and increasing the reflectivity of urban environments to get that heat reflected back into the atmosphere. Trying to understand what the current reflectivity and absorptivity of a particular urban area is a first step, and using machine learning and satellite imagery to do that, and then to map out what the reflectivity potential and then the optimization of how to and planning of how to deploy the distribution of reflectivity across an urban area is really the opportunity that the World Resources Institute and AI for Earth are going after in this case. But I just wanted to stop there, actually, so that we have enough time for Q&A, and turn it back over to Asta and I for answering some questions.
Thanks, Lucas. Thanks, Asta. We do have a few questions, and I hope that others will continue to submit questions for this session as well as for the rest of the sessions throughout the day. The first question is from Adam Stewart, and it's for Asta. Adam asks, how does the inkjet printer sensing work? Does the printer need special ink, or does it work with standard ink cartridges? Also, what's the latency time for the hair color sensing? That might be especially important for Lucas.
Okay, great. So thanks for the question, Adam. So what we did is we used one of those Epson printers that have individual ink cartridges that you can pull in and out. And our chemist, Biklin Nagayan, and Sifei Chen, our physicist, were able to generate those inks individually and then pour them into the cartridges. And then we would print out the patches and coat them with a resin so they wouldn't start changing. As far as latency with hair, it is instant. It is actually, it looks like magic. We were out filming a video of it, and as soon as one of our models walked outside, his hair changed instantly. So it's kind of like magic.
That sounds magical. I have a question for Lucas. This will be my own question for you. As the person overseeing Microsoft's environmental issues and AI for Earth, I wonder if you could share your own bias as far as what types of partnerships you are most interested in seeing for what's coming up for AI for Earth. What do you think is missing? What do you think are priority areas that we should really be stimulating and collaborating with other researchers on?
Well, I think the opportunity for large-scale deployments is probably the most exciting part of the next phase of AI for Earth, and where partnerships become so important. I've shared, I shared 3 of my favorite projects, particularly in the urban space. I've got, a handful, maybe 10, 15 more in the broader AI for Earth portfolio that I think not just have the potential to scale, but already are scaling through partnership deployments. So many of the others have so much potential, but are still looking for that right opportunity, that right city or municipal planner, that right country level government official to work with, to take their solution and put it into a more formalized planning process and deployment process. And so that's really where my mind is at right now, is a bit of a matchmaker role. Really from a partnerships perspective of saying we already have a fantastic community of grantees. We're going to continue to grow that, make no mistake about that. But where I think that Microsoft can really help play a role now is ensuring that we're connecting those solutions that are being built up with our community, with the people and the organizations that need them most. And that was one of the reasons that I was really interested in this workshop, is being able to get that message out.
I want to push you just a little bit harder on that, Lucas. Could you share a little bit more about the role Microsoft plays or doesn't play with these partnerships? Is there an expectation that awardees are going to have some level of hands-on engagement from someone in Microsoft, whether it's you or Azure or research or anywhere else in the company? Or is it more, here, go do your great things, we believe in your ideas, keep us posted sort of thing?
It's kind of a staged approach. It's actually, there's options in all three categories that you just mentioned. You know, I think about this very much like a funnel process. We have just apply to AI for Earth. It's a very simple application process. You can go on our website, fill out a short form, and get free access to Microsoft Cloud technologies. It's really, that's where everything starts. Then from there, we start looking at what people have achieved and what their needs are and where the opportunities for scale are. If there's a requirement for additional education or to get to know each other better, we look to invite them into the AI First community more generally. We hold AI First education sessions, including historically at least, and we'll likely revert back to doing this when situation allows, in-person education sessions inside at Microsoft to bring everybody together. But then we also have a dedicated data science team for AI for Good and for AI for Earth, where for high particular projects with particularly high potential for broad scale deployment, we do have opportunities to work directly with our team of data scientists to basically code hand in hand and build deployable solutions.
Got it. And I realized in my selfishness in wanting to get my own questions asked, I was overlooking several questions that came in. So with 2 minutes to go, I'll rapid fire some questions to you. I think these are all for Lucas. And if we're not able to get to all of them in the next few minutes, Lucas, hopefully you'll have a chance to respond to them individually. Jamie Ponce from City Tech asks, fantastic examples of current and emerging tech and partner applications. Thank you. Could Lucas and Asta please speak about key criteria for climate environment partnerships and how they tie back to core business goals?
Sure. I think, you know, from how these things tie back to core business goals, I would say that the way that Microsoft looks at the climate space and the sustainability space all up is an extremely inclusive view. You know, I think at the highest level, kind of the most existential level, I think Satya said it best a few months ago at the start of the COVID-19 crisis when he said, for Microsoft to do well, we need the world to do well. And so that's really kind of at the highest level, the way that we think about this. And we're pretty convinced that if our global society doesn't get out ahead of our climate challenges, then the world isn't going to do well. And we also, though, believe on the far opposite side that our technology and our business model has the potential to allow us to get out ahead. I think, you know, software is the most malleable kind of thing that humans have ever invented. It's the most scalable, and our ability to deploy what we like to at least think we're good at, which is software engineering and cloud scale artificial intelligence platforms. We think that that's a currently underinvested in area, even if it might not be the silver bullet to solving our challenges. And then, of course, fostering that ecosystem of partners. So for us, it really goes everything from the risk to the reward side of working in this climate space, and it's almost impossible for us to separate those things out.
Great, super. Well, that's all the time that we have for questions right now. As I mentioned before, I hope that you'll have a chance to respond to other questions because we did get quite a few. Thank you both very much for your time and for your thoughtful comments.
All right, we will now be moving on to our next speaker. We'll next be joined by Brenna Berman, who is the CEO of the City Tech Collaborative. Brenna will be talking about the role of collaboration in city innovation.
So the first couple of speakers who I found super interesting really set the stage well for, this is not working at all, for what I want to talk about, which is the role of collaboration in city innovation. And because they mentioned a couple of things around, Lucas talked about the importance of the different Microsoft partners and the work he's been doing. And in the last work around carbon emissions, they talked about the next step in their work being engaging directly with cities. That they wanted to engage directly with cities and mentioned how it can be challenging to build that connection directly between academia and city government, which is something I certainly know well. So why don't we move to the first slide? And in our work at City Tech, collaboration is actually what we do. We're an urban solution accelerator that works in a number of areas, including in air quality, but we work in mobility as well, which is a related space, and infrastructure security, and health and human services as well. And what you're seeing here is really, what's probably not going to be surprising to anyone in our work today, but is how complex the urban environment is, right? You have an incredibly diverse number of stakeholders who all have a voice and opinion and frankly, something to add to the work that goes into creating an urban solution from, the residents and local government, corporate and startup investors and innovators to the civic and academic institutions and the visitors and tourists that someday will be coming back from city to city to share, in the work that goes on there. And when we talk about cities, we often talk about them as one thing, but I think we all know that isn't true, right? Cities are made up of residential neighborhoods and business districts and industrial zones, as well as green spaces. And so, the work that all of us do in cities is actually going to play out differently in those different types of localized areas, depending on where you're working. And the challenges that cities are facing are increasing, no more now probably than any other time in history, right? And city governments and people who invest and care about cities are focused on everything from economic development and job creation to challenges with aging infrastructure and how to fund new infrastructure, to transportation challenges, flooding and heat waves, and access and equity to the people who live in those cities. So it's a very complex backdrop that urban innovation has to occur in. And frankly, it's unlikely that the solutions that are going to make cities happier and healthier and safer places to live are going to come from one organization alone. And that's where, City Tech comes in. And amid all of this chaos, if we move to the next slide, there really is some organization there to help us understand what cities look like. And what you're seeing here, and there is a build in this slide that you can go ahead and click through. There's clear pieces of cities that I think have been understood pretty deeply over time, right? There's physical infrastructure, which are those urban spaces where we live and work and play and that we can see and touch, the buildings and the bridges and the roads and the park spaces. And more, and probably where almost everyone on this call is working, there's the data and digital infrastructure and all of that information and foundational IT capabilities that are producing more and more data every day that can help us better understand our cities and the people that live in them. And finally, there are those public and private services that may come from business or government or civic organizations that are there to meet the needs of the businesses, organizations, and people that live in cities and that drive vibrant economies. In between those structures that make up our cities are opportunities to improve life in those cities. That's where City Tech focuses on bringing groups together to create solutions. And those range from everything like sensing networks. I think I've seen more examples of innovative sensing networks in the last hour than I've ever seen in my life. And that's where you see hardware and software coming together to create new data from the built environment to understand real-time conditions and needs and opportunities to improve life in our cities. And then leveraging that data coming from the sensing networks with any number of advanced analytical approaches to drive data sharing or aggregation and storage to better understand and drive new insights into urban life. Again, I think the aim is the same in any city, which is to make that city more livable. How you define livable is going to be tightly related to the culture of that city. And finally, an area that is frankly, I think, more emerging than the other two, which are sort of fully here in our world today, is how urban design is changing and developing because of the availability of data and technology as a practice. And urban design really speaks to the development and management of those public and private spaces, and how you can create a city that meets the needs of the people that live there and the businesses that need to thrive there. And this really is the construct that City Tech uses to understand the opportunities that are available to bring technology and partners together to solve large urban challenges. And I want to talk a little bit in the next slides around how we think about collaboration and who those parties are, and then a couple of quick examples of problems that we've been able to solve through those partnerships, and how we think about what makes a successful collaboration. If we could move to the next slide, please. One more. Thanks. So just quickly a little bit about who City Tech is. As I mentioned, we're an urban technology accelerator. We do tackle those public problems or business opportunities that are really too big for any single organization to tackle alone. We focus on creating cross-sector teams to develop scalable, market-ready solutions. Pilots are wonderful. We use them as a development approach, just like a lot of other organizations, but we don't stop there. We want to make sure that any solution that we build has a clear go-to-market approach to help as many cities as possible. We focus on all of the industries, frankly, that help shape urban life. At the moment, most of our work really touches on the areas of mobility, health and wellness in cities, and quite a bit of work these days in like the connected construction and infrastructure space, and really those hard structures that shape urban life. We were born and raised in Chicago, is what we like to say, but we've worked in cities all over the country, and really every city is a potential partner. Cities can be very unique in their culture and the challenges they face, but a lot of the solutions that they need have similar components. If you could give me the next slide, please. When we think about the partners that make a difference in cities, a lot of them are really easy to come up with, like the role of local government and civic institutions. Some of them, and what you're seeing here is a picture of all of the types of partners that we try to bring to the table in the formation of a solution. Some of them are a little bit sort of less well known maybe when you think about the partners that you need at the table around a given solution. Many of us, I think, would expect our utilities to be important in a city, right? We've already talked about some of them today in some of the previous examples. When we think about some of the technologies that are important, the role of platform providers from a cloud or ERP perspective is also quite important and probably jumps to mind right away. But the role of financial services might not, right? Many times when you're thinking at city scale, you do begin to move into the realm of large cyber physical systems, right? When we talk about the importance of, smart solutions around infrastructure, right? The importance of technology as you're building new bridges or roadways, those become major capital financing projects. And so understanding the role of financial services and investment around that project becomes quite critical. So what you're seeing here is just a view of how broad the set of partners are that need to be at the table to form a collaborative strategy around a given solution or strategy of innovation for a city. If you move on to the next slide, what you're seeing here is just a take at the moment of the partners that we we are working with, and you'll see, frankly, some very big ones. Our host today, Microsoft, has been a longtime partner of ours, and the breadth of capacity and capabilities that Microsoft brings to the table is something that we rely on every day. But you'll also see here, broad philanthropic funders. You'll see small startups, and you'll see government organizations which have already been mentioned in a collaborative capacity like NASA and Argonne National Laboratory. So it's a broad swath of organizations from large to small, to public to private, to community organizations that are required to answer the needs of cities. And I think what's most interesting when you sit back and look at a city problem, when you're driving home tonight through your own city and you see something that kind of bugs you on a regular basis and you say, someone should do something about that, I would challenge you to sit back and say, who is that someone? And I would argue that it's probably a plural someone. And the challenge that City Tech really came about to answer was the convening factor around who those someones were was a missing piece. And then aligning how those someones work together was always a challenge. So what you're seeing here is really that broad swath of partners that we tend to work with on all of our projects. If you could move on to the next slide, please. And the partners aren't enough, right? If you could imagine for a minute, on any one of our projects, we bring together anywhere between 6 and 12 of the circles you saw on that last slide. And if we just put them in a room with a giant big whiteboard and a bunch of markers and said, help us, lower the level of carbon emissions in the city of Chicago, if I came back in 2 days, I think I would have a bunch of starving partners on the floor and not a lot of work having been produced. You need to provide a proven approach to bring a collaborative ecosystem together to produce results. And that's what you're seeing here is just our approach to how that works. And we always start not with what we think the solution should be, but what the problem is. And that may seem very obvious, but when you bring a number of partners together, they don't always have exactly the same understanding of that problem that we're trying to address. So we spend quite a bit of time decomposing that problem and coming to a common understanding of what we're actually trying to address. And then we move into the solution definition of how we think we can fix it. Testing that solution, and then spending quite a bit of time working through how to scale that solution to address that problem at the city level, and how we can scale that not only within a single city, but scale it across cities from a market perspective to make sure that solution has legs from a scalability and marketability perspective. And there's not a lot of magic here. There's a lot of hard work, because what you're seeing built into these 4 little circles is where you need to answer questions like, who owns what part of that solution? Whose IP is getting investment here? Where is new IP going and who owns it? Those are very, very tough, frankly, very closely held questions for public and private partners that need to be solved before you can go forward and integrate a new solution. Next slide, please. So it's easiest for me always, and I think many people, to think through an example. So I thought I'd go through 2 quick ones, one on the green infrastructure side and then a mobility one next. So Chicago, like many cities, has challenges with water. I think I consider water to be a Goldilocks problem. Almost every city has either too much or too little. Chicago has too much, and every time it rains in Chicago, at least some of our neighborhoods flood. And this is a challenge around the capacity of our traditional water sewer infrastructure, which over the years has been expanded as much as it possibly can be. So over the last several years, we've expanded our interest in implementing alternative water management solutions, such as green infrastructure, which includes things like permeable pavement, water controlling planting solutions, and bioswales, all of which basically hold rainwater and slow its dispersion into the traditional water sewer system to prevent things like flooding. The city of Chicago has been interested in investing in green infrastructure for some time and simply didn't have the data to optimize that investment. And as you can imagine, green infrastructure at a city scale is not a cheap investment. So City Tech brought together a number of partners, and you're seeing them listed above, to create a green infrastructure monitoring system, which would do two things. One, it would create investment data from a number of pilot locations to understand the impact of green infrastructure on traditional city infrastructure, so that the city could make optimized investment decisions on how to move forward with green infrastructure as an integrated component of the water management system for the city. And it would also inform new management processes for that green infrastructure as it became part of the integrated water management system of the city. And to give you an idea of the breadth of these partners, so you're seeing Microsoft first, who stepped up to provide the secure network and data visualization dashboards to both collect, manage, and analyze the data that was coming in. The City of Chicago was an active partner in this, actually across a number of departments. You would expect the water department to be a partner in this project. It may not be surprising about how big a partner the IT department needed to be in this project. This project represented what became the largest green infrastructure or environmental data set to ever be shared publicly at the time. The City of Chicago, or the IT department, not only had to partner more closely with the water department to help them manage the data that was coming in from this project and turn it into a management tool for the water department, but they had to rebuild the city's open data portal in order to be able to share a data set of this size so that other cities could also benefit from what the city was learning. Senformatics and Opti were two smaller companies. Opti is a relatively small startup out of Boston that came forward with hardware and software on the sensor side in order to collect the data that was embedded in the green infrastructure to sort of spearhead the product. And then AECOM is obviously the global engineering firm who actually was not involved in the construction of the project, but involved in the go-to-market part of the project. They actually carry this solution, which is now an integrated package of sensors, secure network, and then in data analytics and visualization back end. They now carry that as a package to customers all over the world and embed that IT package essentially into physical green infrastructure projects in the US and beyond. And then West Monroe Partners and their environmental consulting practice advised on both the original architecture and the analytics of the data as it came in. So I think it's fairly clear to see that, you know, there would have been no way to produce such a robust project design or impact for the city without these like broad set of partners. If you could move on to the next slide. Sorry, this actually just goes across the outcomes, many of which I talked through. At the end of the day, we ended up with a new sort of sensing technology that meets the challenges of data collection across a decentralized water system that is now carried to market through the partnership with AECOM. The new data sources specific to the City of Chicago are now available to them to drive like future design and management in the water system. There's a new capability around collecting green infrastructure performance data, which is embedded in that system. So if you think about it, Chicago's not the only city that's asking questions about green infrastructure. If you had a company like Opti, which only sells the sensor, show up at the door of the water department in the City of Chicago, you know, the City of Chicago understands their problem, what they're trying to answer. You know, Opti has a great set of sensors that can collect that data. The City of Chicago does not have the capacity or the capability to implement that sensor and integrate it directly with a network and drive those insights itself by buying a sensor. They need that full solution that addresses their problem. And that's what this project does, is it does that solution integration so that there's a full answer in the marketplace to the question that the City of Chicago and other cities are asking. And that's kind of the magic of this collaborative approach. Next slide, please. And then one more quick example, more from the mobility space. And I want to give you an idea of timeline. So again, you see the number of quick partners at the top. MasterCard, the Chicago Transit Authority, Ideas 42, which is a behavioral economics consulting group, and Cineverse, which is a text-based communications group. For anyone who is familiar with Chicago or baseball, when the pre-COVID, when the Chicago Cubs have a night baseball game, the capacity on Chicago's red line, which is our northbound train line, reaches a point of not only being uncomfortable for the passengers who are packed into trains as sardines, it is actually judged by the transit authority to be unsafe for those customers, and it puts undue pressure on the physical structure of those trains. So basically, you end up with a transit system that is past capacity during rush hour because of that special event. You end up with longer train times, frustrated travelers, and some pretty deep safety concerns. The solution was to try and come up with a tool that could communicate directly with those riders to help them change their behavior and basically travel earlier or travel later, but not leave public transit, because you certainly don't want to lose ridership and push them off into other modes of transportation that have implications like increasing or decreasing air quality, increasing emissions, et cetera. The outcomes on this one were really interesting. We had more than 2,000 participants opt in to a 2-week participation period. This was done through text. Because of how you pay for public transit in Chicago, we have the ability through the CTA to reach out to riders. We had a 17.5% reduction in ridership during the opt-in period, which means that peak in ridership that was causing the longer travel times and the frustrated riders and safety concerns was lowered by nearly 18%, which is a huge impact on those sort of negative problem statements that were coming out of the increased ridership. So this was proof that essentially you had a very easy, cost-effective way to lower, ridership at a peak time without pushing those riders off into other means of transportation. And this was a really strong blueprint for public-private partnership for the transit authority that they've been able to repeat around other challenges as well. This was also a very fast, easy pilot, especially in the world of transportation, where usually they focus on supply side changes, which means adding trains, adding lines, adding buses. Those are all very infrastructure intensive, expensive solutions. This was a demand side solution, which we were able to define, pilot, and provide results to inside of 6 months. So in the world of infrastructure and transportation, this was a very fast, light, and affordable way for them to think about improving rider experience. Next slide, please. So again, looking quickly at the outcomes, right? 2,000 participants and an 18% reduction in ridership during not just peak time, but in what was actually a very uncomfortable and unsafe rider experience, and creation of a tool that the CTA could use anytime they had basically a special event. This particular capacity, if you think about what happened after, this particular capacity was reconsumed by MasterCard and incorporated into a set of analytics they offer to other transit customers. And then moving on to what I believe is the final slide, to think a little bit about how to think about collaboration in multi-party innovation in general. There's really 2 critical elements to think about, and one is the importance of carefully curating that ecosystem of partners. So going back to that thought exercise that I asked all of you to think about when you're driving home tonight or walking through your own town, is who are the partners that you would bring to bear to solve a problem in your city? Who are the partners that you need? But identifying those partners isn't enough. How do you align them to actually drive collaborative innovation and solve that problem? And what you need to think about is how you get them to a joint understanding of that problem. How do you align their incentives to solve that problem? Because when you have a room and you fill that room with government executives on the one hand, corporate executives on the other, some community groups, some residents, and an academic expert, they're not all driven by the same incentive. So how do you align them to solve that problem in a way that benefits the city? And then how do you leverage their unique capacities to co-innovate on a solution to that problem and include the residents, the technology, and an investment required to build a scalable solution? So this is a collaboration in an urban setting, is a complicated process, but it is a process that yields a very unique approach to solving intractable problems, which is where, frankly, where cities are today. This leaves us, I think, with a little bit of time for some questions. And thank you so much for the time to speak to the group today.
Thank you, Brenna. I really appreciate your final note there on taking an ecosystem approach. It reminds me not just a little bit about trying to work with researchers in Microsoft who have diverse perspectives and agendas and trying to get them all to work toward common goals. But with persistence, we get there, right?
Yeah, absolutely.
So we have a couple of questions for you. This first one comes from Eric Gordon. He asks, where do organized community groups come into the cross-sector model for finding solutions? Yeah. Oftentimes, what's good for the public and private sectors are not good for the public.
Yep. Eric, you're absolutely right. And I think that's where, it's a really easy bullet for me to type that says align incentives. That's probably the hardest step of our process. So community groups are invaluable in this process. They're oftentimes the organizations on the ground that actually are working most closely with residents, who actually know how problems are perceived or experienced by those residents, and who are most able to articulate that experience, sort of at the table as you're designing a solution. I think I might disagree with you a little bit that what's good for corporations is always at odds with what's good for residents or good for the public. I think you can, and I don't mean to sound too Pollyannish, I don't think this is easy. I think you can find a middle ground where you can build a solution that has go-to-market value for a company and still delivers what is needed by the residents or by the city. Again, I don't think that that's easy, but I think it can be done. And frankly, I think you saw that with the smart green infrastructure example, right? That did begin to, it's not fair to say it eliminated flooding in Chicago, but it did begin to reduce the challenge of flooding in Chicago, and it created a strong go-to-market solution that is making money for AECOM and Opti, so they have every incentive to bring that to market in their businesses. So I think that actually did both, and it's quite affordable. It did not drive up the cost of, I think it's $14,000 for the full package of tech and sensors. So I think that's an example of there can be a win-win. It is not easy by any stretch.
Great. We have time for one more question. This one comes from Scott Counts. Scott says, awesome talk, Brenna. How can we pair your expertise in making collaboration and solutions realized and high impact with the great scientific work on urban air quality we've seen over the last few days?
So, I think that's exactly sort of why Microsoft pulls together 3-day research organizations like this, is we're hoping that kind of outcome comes from this. Microsoft is already a partner of ours, so we're already talking with them about some things that could happen in the fall in Chicago. That's a to-do, I think, that I would love to take away from these 3 days is, beyond Chicago, beyond any individual city, how do we pair the amazing research that's going on, not just within Microsoft, but in some of the other examples that Microsoft has helped highlight today? How do we move from research project to sort of implementable city solution together? And that's something that City Tech has been thinking about and working on, for a long time. So I think there's a to-do of let's have that conversation and just get on the phone and talk about how we make it work. I think we have those two pieces. We just got to bring them together.
Great. Well, it's good to have the right recipes or the right ingredients for the right recipe.
Yep. We just got to bake the cake.
That's right. All right. Thank you very much, Brenna. Very much
Thanks,
appreciate your time and your comments. And
thank you.
Talk. Okay, we now will invite Jocelyn Turnbull, our final speaker, to join us and share her thoughts. Jocelyn is coming to us all the way from New Zealand, so we appreciate her, what I believe is a very early start to her day, 5:30 a.m. if I'm not mistaken. So I'm sure everyone will forgive Jocelyn if she needs to rub her eyes a little bit through the course of this talk. Jocelyn, the microphone is yours, and thank you again for joining us.
Great. Can everybody hear me?
Yes, we hear you loud and clear.
Great, thank you very much for having me, and also thank you to the last couple of speakers who've really provided a bit of background to what I'm going to talk about. So I'm going to talk about thinking about an integrated system for urban greenhouse gas monitoring and assessment. Okay, sorry about the technicalities. So I'm going to divide my talk into two parts. I'm going to start off by talking about the methodologies of how we can evaluate urban greenhouse gas emissions, and I'm going to use the Indianapolis Flux project to as an example to explain that, and that's, you heard a little bit about that from Kevin Gurney earlier this morning. And then the second part of the talk, I'm going to think about how we can integrate what we're doing in terms of the science with policy and policy outcomes. And so Brenna's talk really dovetails very well with what I'm going to talk about here. And for that, I'll use an example from here in New Zealand, from Auckland, of work that we've been doing of trying to integrate with policy. So starting with the methods for evaluating emissions from the Indianapolis Flux project. This is a project that's been running for about 10 years. We started in 2010, and we have a whole host of different measurement techniques and data products and modeling that are involved. So what I'm going to do is walk through three different methodologies and then throw in a little bit of complexity of splitting out by source sectors. So we already heard from Kevin Gurney this morning about what we call bottom-up data products. And in this case, this is the product that Kevin developed called Hestia, which is this very high resolution product that uses emission estimates and then a whole bunch of ancillary information to disperse those emissions across a city in both space and time. So I'm not going to go into more detail on that because we've already heard it, but we start with this very high resolution product. But we can also do a bunch of things in the atmosphere. And so I'll talk about two methods. The first one is we call an urban mass balance. And you can think of this as a hosepipe method or a tailpipe method, perhaps. So this is a way of getting at emissions from a whole city, and it can also be used for other things, like it's been quite commonly used to look at methane emissions from natural gas fields, where there's a whole bunch of natural gas wells and so forth that are emitting methane. So you can imagine that you've got a city that's producing emissions of CO2 or whatever other gas you might be interested in, and you've got the wind flowing over that city. So the wind comes from a background, you've got a background concentration of the gas you're interested in that's coming in as the air enters the city. Then it flows over the city, and those emissions from the city go up into the air and change the concentration of the gas in that air. And then it flows downwind. And so what we do is we'll fly an aircraft downwind of the city to actually observe that tailpipe. And in the bottom here, you can see on the left is what we actually measure. We'll fly the aircraft and transect across the downwind area of the city, and we'll do transects typically at several altitudes downwind of the city. And what you see in that picture on the left there is that we see much higher CO2 concentrations over the city area where that plume of polluted air is coming out of the city. And so that's what we're actually measuring, and we use that to basically diagnose the shape and the flow of that tailpipe of air coming out of the city. And on the right, you see how we basically take those measurements that we've done on the left, and we use some sort of method to fill in the gaps so that we get a full picture of what that tailpipe looks like. In this case, we used a method called kriging. There's a lot of different ways that one can fill in the gaps, and that's potentially something that this group here today might be interested in. There's a lot of data methodology for doing that very well. So this method is really nice in that you can have one plane or maybe a couple of planes that are instrumented with these quite expensive, quite complex instruments, and you could potentially go around to many, many different cities and measure emissions. The downside of this method is that we get a whole city flux. We don't get that kind of spatial resolution that you get from the bottom-up inventories that Kevin showed. And also, if you are flying around many cities, you're going to get a snapshot in time from the city that you look at, rather than being able to follow how the emissions are changing through time. Of course, you could go out and fly these aircraft measurements as often as you can, but realistically, it's never going to get cheaper if you do it routinely over a city, whereas some of the other options will get cheaper over time, because once you've got the infrastructure and you don't have to keep deploying it. So in this case, from Indianapolis, we've done this work, and I'm showing there how one actually gets from this curtain of measurements that we've made downwind of the city through to actually calculate an emission flux from the city. And that's the equation on the top left there. And basically, it looks like a complicated equation, but basically we've got this curtain of measurements downwind of the city. And if we also know what the wind speed and wind direction is, we plug them into an equation and we end up finding out what the emission flux is from the city. Just the same as with a hose pipe. If you know the diameter and the flow through that pipe, you can work out how much water is being pumped out of wherever it's coming from. In this case for Indianapolis, what we did is over a period of about a month, we did 9 flights over the city. And what you see there in the little graph is what we calculated for the emission flux for CO2 on the bottom in black, and CO, which is carbon monoxide, on the top in blue, which we also measure. And there's some variability, but not that much variability of the flights. So we can average that over that period to get an estimated emission flux for the city. And I'll come back to the carbon monoxide in a couple of minutes. We're interested in carbon dioxide, CO2 mainly, as the main greenhouse gas, but we'll use the carbon monoxide as well. So that's the first atmospheric method. It's very appealing in the simplicity of it. But now we get to the second method, which we heard a bit about from Ron Cohen yesterday, and Kevin Gurney alluded to this morning as well. So this is what we call a top-down atmospheric inversion. And in this case, we're doing it for an urban area, but we can do it at basically any scale, and from the global all the way down to very small scales. So what this does is it takes a series of observations and some modeling. So showing here on this first slide is the observations that we're doing in Indianapolis. So the photo is of Indianapolis looking to the west from the eastern edge of the city. You can see in the background in the haze, the pollution, you can see the downtown of the city, and of course a large motorway. This is I-70, I believe. Or if anybody's from Indianapolis, you can correct me. And what I've circled there in the yellow, that is one of the towers that we're using for measurements. So Indianapolis is flat, so we don't have places where we could put instruments on high points. Instead, we use mostly cell phone towers and some other towers. In this case, this is used by the police and other law enforcement to get information passed around the city. This particular tower is about 150 meters tall. But we use towers anywhere. The lowest ones are about 40 meters tall. Because we're working with other people's towers, we have to be flexible of the height. But we want to go for towers that are high up where we can get a good view of the whole city. And on the bottom left there, you see the map of where we have towers. We have 12 towers running in Indianapolis. And on the top left, you see the observations of CO2 from some of those towers through time. And what you see there is a seasonal cycle going up and down. That's the earth breathing. I'll come back to that in a minute. You see a long-term upward trend. That is the climate change, the increasing CO2 in the atmosphere. And then what we're interested in for the city is sort of that noise on top of that, of the difference amongst the different towers. That's the emissions within the city. So I wanted to just very briefly talk about footprints and thinking about the network design of where one puts our sampling sites. So the map here just shows what we call footprints for 5 of the towers in Indianapolis. So the grey is the background, the city and the city emissions. And then the coloured blobs are the footprints for each tower. So what the footprint is tells us based on the height of the tower, its location, and the winds, and the topography as well. And that topography can include building topography. The footprint or the influence of the surface of the earth that's observed at that tower will vary depending on all of those things. And so you see in this picture, you see these kind of like paint splatters. Those are because this is averaged over a year of time. So with different wind directions, each tower will see a different part of the city. and it will have a certain footprint depending on how high up that tower is and where the location is. So if you want to cover a whole city, you need to have enough sampling sites at the right locations to be able to have footprints that overlap and cover the whole city. And so if you do the kind of instrumentation that we have here in Indianapolis, you would have a few towers that are tall. If you do the kind of thing that Ron Cohen talked about yesterday with a lower cost dense network that's closer to the ground, you might need a lot more sensors to cover the same spatial area. And so then we do an atmospheric inversion. And just to explain a bit about this, the way an atmospheric inversion works is to combine these observations with a bunch of modeling and with what we call a prior. So we start off on the left there with a bottom-up data product or inventory. And so that's the kind of Hestia data product that Kevin showed us earlier this morning. And so that comes with a spatially resolved and temporally resolved map of emissions. And then we use an atmospheric transport model that's driven by either modeled winds or by actual meteorological observations. And what we do is we simulate how the air will move those emissions to the sites where we're actually making measurements. And then we get a set of simulated observations for each site. And then we have our actual observations. And we compare those two. And then we do an optimization, which is the inversion. And that's just a mathematical optimization. And from that, we come out with and say, how should those prior fluxes, that bottom-up data product, how should they be adjusted so that we get the best match of our simulation with the actual observations? And that gives us a final product, which is basically, it's a refined version of that initial bottom-up product. So there's really a lot of feedback between the atmospheric observations and what we think we know from the bottom-up. And so in this case for Indianapolis, I've talked about the three methods, the bottom-up, the inversion, and the mass balance from the aircraft. And here's the results from 3 different studies using those 3 different methods in Indianapolis. And they agree not too badly, within about 20%. That's all right, but it's not really good enough. But it's important to understand that we're not actually comparing apples with apples here. These 3 different methods have a lot of differences between them, from the simplest, that we're actually not looking at the same time period. Maybe the emissions are different at different time periods, through to some more complex things. So I'm not gonna talk about all of those things, because all of those differences, because some of them are pretty simple, but I'm really gonna focus on what we're measuring. So the bottom-up product Hestia is only looking at the fossil fuel emissions with a little bit of bioethanol that's used in fuel, whereas the observational methods measure all the CO2. So what we want to do is be able to look at the fossil fuel CO2, which I've denoted here as CO2FF, so that we're actually comparing the same thing. And I'll just divert a little bit for those of you who are not familiar with the carbon cycle to understand what I'm talking about. So the global carbon cycle, we have CO2 in the atmosphere that's increasing over time due to the emissions of fossil fuels. We have natural carbon exchange between the ocean and the atmosphere and the biosphere and the atmosphere. That biosphere and atmosphere is the earth breathing. That's photosynthesis, removing CO2 from the air, and respiration, returning it to the air. And that can be seasonal. And those are really big fluxes between in and out between the ocean and the atmosphere and the biosphere and the atmosphere. But over the year, they come out roughly even. Roughly net zero. And then we have fossil fuel burning, which is actually a smaller amount of emissions than those other sources, but it's a one-way flux. It doesn't go back into the ground, at least not over timescales of thousands of years. It takes millions of years. So when we're looking at CO2 over a city, we want to be able to distinguish that fossil fuel emission, which is what's driving the increase, from that biogenic flux, which is net neutral over the year, but on a day-to-day basis can be very large. And as Kevin alluded to a little earlier, the way that we can do that is using radiocarbon. If you're familiar with radiocarbon dating, you'll know it's used to find out how old things are. And we can use it to figure out how much of the CO2 that we observe in the air comes from fossil fuels. Basically, radiocarbon is produced in the atmosphere by cosmic rays. It goes throughout the carbon cycle, and it decays radioactively. So the natural processes, the exchange between the land, the biosphere and the atmosphere has roughly the same amount of radiocarbon in it because the turnover is very fast. Fossil fuels, on the other hand, are millions of years old and they have no radiocarbon left in them. So it gives us a tracer for fossil fuels. And just to show you that it does work, or it should work, this is a map of the global distribution of radiocarbon at the surface of the Earth, or radiocarbon and CO2 on the left, and on the right is a map of fossil fuel CO2 emitted, and both of these are emitted and transported in a model. And you see that these two maps look really identical. The sources of fossil fuel CO2 really map to produce this spatial pattern of radiocarbon in the atmosphere. So back to our Indianapolis example. Lots of data here. I hope I don't scare those of you who are not scientists. So I'm showing on the left is the radiocarbon measurements, and then in the middle is carbon dioxide itself, and on the right is carbon monoxide. And then in the bottom panel, I'm showing the enhancement over the city. So for CO2, if you look in the middle, this is, I take the black points in the top line, which is the tower upwind of the city, and subtract them from all of the other tower measurements, the other towers, or the colored lines. And so you see then an enhancement over the city, and from the radiocarbon measurements on the left, we get the fossil fuel CO2 enhancement over the city. And then we can take this information and we can just do correlation plots. So here on the left, I'm showing a correlation of the enhancement in CO2, or the excess as we call it, on the y-axis versus the fossil fuel CO2 on the x-axis. And then on the right, it's the carbon monoxide excess versus the fossil CO2. And you see very good correlations between these. But what you see for the CO2 excess is that their correlation is not one-to-one. So if all of the CO2 that was coming out of the city was from fossil fuels, that would be a one-to-one line. But in fact, we see a little bit more CO2 coming out than is due to fossil fuels. And so that means there's actually some biogenic CO2 coming out. And that turns out to be roughly 10% of the magnitude of the fossil fuel emissions in Indianapolis in winter, which is the time period we're looking at here. And so that's coming from respiration. There's humans and their pets are respiring, and also from biomass burning, which can be things like people burning wood in their fireplaces. And then on the right, that relationship between carbon monoxide and fossil CO2 is really useful because carbon monoxide is co-emitted with fossil fuel CO2 during burning. And the rate of emission depends on the particular combustion conditions and whether there's, for example, catalytic converters on vehicles. So if we know that ratio, we can actually obtain fossil fuel CO2 estimates at high resolution because we can measure carbon monoxide at high resolution. So when we use that information, we can actually adjust those different methods that I showed before to get an apples to apples comparison of the fluxes across the different methods. And then what we see here, so the bottom up inventory, the inversion adjusted, so it's just looking at fossil CO2, the mass balance based on just fossil CO2, and now I've done that in two ways using either CO2 or CO. These all agree within 7%, which really starts to be useful for looking at changes in emissions. All right, so I'm going to switch to the second part of my talk, which is about how we can really address policy questions. And so I wanted to talk about the World Meteorological Organization's program called the Integrated Global Greenhouse Gas Information System, or IGGIS. And this is one of a few programs that's really trying to think about how to link greenhouse gas monitoring and assessment programs into policy. There's also some programs, NIST in the US, CO2 USA, which is a science-led initiative, and ICOS is a European program that are all doing similar kind of things of trying to figure out how we can link together what we're doing in terms of observations and model products with what policymakers want. And IGGIS in particular has some example programs that are used to sort of highlight how to do this. So one of the key things for policymakers to use this information is that if we just tell them, here's our results, they don't quite know what to do with it because they have a set of guidelines that they need to follow. At the national scale, the IPCC has something called the Task Force on National Greenhouse Gas Inventories. That's like the Bible of how nations report their emissions to the United Nations and as part of the Paris Agreement. And so one of the things that we've been doing is that in 2019, those guidelines were updated and they include a much more detailed role for these kind of atmospheric observations to be included in reporting. At the city scale, it's less set in stone how one reports emissions. It's still voluntary, but many cities, through many of these different groups like C40 Cities and the Global Covenant of Mayors and so forth, many of them are using this GPC, a Global Protocol for Community Scale Greenhouse Gas Emission Inventories, which is kind of based on the national scale inventories, but a little bit different. And so we can use our atmospheric information to really improve upon the bottom-up inventories that have traditionally been reported, and to really, track down where there might be issues and ways to improve them. This is just an example from the UK of an air conditioning gas, which is also a greenhouse gas, called HFC 134A. And the purple is what the UK was reporting for their inventory. In the coloured lines at the bottom, you see what's based on the emissions based on atmospheric observations and an inversion. And based on that information, the UK has then revised downwards their emissions of HFC 134A. They're still not quite getting to the point of what the atmospheric observations say, because they're trying to use a slightly different methodology. But nonetheless, those atmospheric observations have really been able to inform what they're reporting. So I guess the initiative to link these things together is working on a good practice guidelines for urban greenhouse gas monitoring and assessment, and those will come out later this year. And the objective is really to provide a bunch of methodology to people of how to do this, and thinking about the kind of situations that one might have and how you might attack the particular problem that you're interested in. This first draft is really aimed at the research community, and in the future that will be evolving into something that's able to be applied more to practitioners, to commercial enterprises who want to do this. So just an example from Auckland in New Zealand, where we're really trying to work with policymakers at 3 different levels. We're working with the national government, with the Ministry of the Environment, and New Zealand has a Zero Carbon Act and a Climate Change Commission that we're trying to provide them information to them. We work with the local councils, in this case the Auckland Council, and then we also work with community groups, and in particular Indigenous groups such as Ngāti Whātua Ōrākei, who have a stake in this stuff. And we went and talked to them, and as Brenna pointed out, these discussions can take some time. And we were a little bit surprised that what they really were interested in is these biogenic exchanges rather than the fossil fuel emissions. They think they have a decent handle on the fossil fuel emissions, but they don't know anything about this biogenic exchange. And that's really been where they want to focus. And there's all sorts of reasons why they care about that. From the Mayor of Auckland has a Million Trees initiative, and he wants to demonstrate that it's great. To the national inventory reporting, the urban biospheric emissions are basically unknown. And from the Indigenous groups, they really care about the environment and how perhaps converting back to native forest would influence what they see. So I think I'm going to skip through, just in the interest of time, I'm going to skip through what I was going to show on Auckland, some more results, and just move to the end to wrap up. To say, so with the methodologies that we're using, we've been able to demonstrate that we can do better than 10% at constraining whole city urban CO2 emissions, and using this sort of combination of different methods, from the inventory-based methods through to doing atmospheric inversions with tower observations, which is what we think of as perhaps the Rolls-Royce of these kind of measurements, or in the world of climate change, perhaps more the Tesla of these kind of measurements, and the aircraft-based mass balance. I talked a bit about how we can separate source sectors, and I showed you the example of using radiocarbon to separate fossil fuel and biogenic CO2, which is really critical if we want to get at emissions. I didn't try to talk about today the opportunity to use other traces that can help us to separate those emissions into even finer details, so traffic versus power plants versus industry versus residential, those kind of things. We can also potentially separate by whether it's coming from natural gas versus petroleum versus coal. And really, to get to work with policy and to make this useful, we really have to have this interaction with policymakers and think about how we can focus our research to really meet their goals. All right, thank you very much.
Thank you, Jocelyn. again, very interesting conversation and a lot of information to absorb. I would like to pick up on kind of your last point there about policymakers, and you gave us some information about how you're influencing policy towards the end of your talk. I wonder if I could push you to just give us maybe another level down of information for people on the call here who have great data, want to get it in front of the right people. What advice do you have for really sort of influencing policymakers when you've got the kind of rich data that you have?
So I have to say that it's really challenging. I think as a scientist, we imagine that everybody is just waiting to get our data, and as soon as we show it to them, they're just going to be in awe and they're going to take it and do wonderful things with it. But of course, that's not the reality. They have their own needs and requirements, and they have a lot of bureaucratic requirements that they have to follow. So what we've found is that it really takes a long conversation, and you have to be prepared to have a lot of conversations with these people. So you start off by maybe you find someone that, some into that policymaker group, and then you just start working on it. You meet with them and you meet with them again and you meet with them again, and that can take years. And one of the things that we find particularly frustrating is that in government, there's often quite a turnover of staff. So you've spent all that time engaging with someone and getting buy-in for what we're doing, and then that person leaves and a new person comes. So it's really about taking the time to work with those people and understanding all those constraints, and then being prepared to be flexible to really think about how what we do can apply to the particular problem that they have, rather than trying to tell them what we think they should need.
So a little subtle manipulation, maybe.
Yeah.
Oh, shoot, we're being recorded. Okay. I have a question here from Kristen. Kristen asks, how do you see the at least 3 approaches you presented for understanding CO2 emissions being potentially applied, understanding air quality in cities for public health?
Yeah, so just a little aside on that what I spoke about is greenhouse gases, and I know for many people, air quality and greenhouse gas issues get conflated, and there are really some subtle differences. That with greenhouse gases, when we care about what the emission rate is, because that's ultimately going to increasing the CO2 loading on the atmosphere and causing global warming, but we don't really care that much about what the concentration is in a given place. Whereas with air quality, we actually care about what the concentration is in a given place where somebody's standing and breathing it in. So there's sort of some subtle differences in how we think about it. But there certainly are some ways to apply it to air quality. I guess I'm not quite sure how to approach that if you're really thinking about air quality or about the greenhouse gas emissions in that question. Maybe you could clarify, Kristen.
I don't know if Kristen can unmute herself for this, but she could potentially write a clarification, and we'll keep an eye out for that. In the meanwhile, I wonder if you could share a little bit, coming from where you are in New Zealand, if you see any influence on your research due to COVID and the restrictions and the geographic sort of dependencies that all of these different systems and networks have.
Yeah, absolutely. So Ron Cohen showed a little bit yesterday. I mean, he used the example of the COVID changes in emissions to show the work that they've been doing in the Bay Area. And we've been working in Indianapolis, in other a whole host of cities around the US to look at this problem, and also here in New Zealand. And we do very clearly see the drop in emissions. And we are still working through it, because the complexity of the changes in emissions due to COVID, it's not just changes in emissions, but changes in how the air is moving, so in the meteorology. And when for example, the wind speed changes, the emissions change, or sorry, not the emissions, the concentrations change, even if the emissions stay the same. And so being able to separate between the changes in meteorology and the changes in emissions is not that straightforward, but we do very clearly see a drop in emissions in most cities around the US of around 10 to 20%, which is consistent with what we expect. Here in New Zealand, we did some side of the road monitoring, and we see a very clear drop in emissions during the very hard lockdown we had here in New Zealand of 80 to 90% in traffic emissions during that time.
Wow. And of course, the big question is what happens when the dial starts turning the other direction, as we've already started to see in some places, right?
Yeah, and that's something we're thinking about here in New Zealand. We're essentially back to normal. There is no COVID in New Zealand, so we're able to start seeing that. And I think there will be some long-term changes. We're seeing very clearly that a lot of people are still working from home, so that's decreasing traffic somewhat over what we had before. But how that pans out over months to years is still unknown.
Yeah. Well, we'll keep our fingers crossed that it continues to trend in our favor, the planet's favor. Okay, thank you very much, Jocelyn. Really appreciate the talk, especially given the hour of the day for you there in New Zealand.
You're welcome.
Thanks very much. Okay, so we now will be turning to our lunch break. We have one fewer speaker today to make some extra room for the report back session that we hope that all of the breakout groups will be a part of at the end of the workshop today. We've got a full hour for that. And I have just a few comments that I'd like to make about that. Our hope is that by the time we get to the report back session, each group should plan to have about 10 minutes for that, which is a little bit longer than we've had in the past. We really want you to focus your report back time on your research plan. We've heard already sort of about the problem statement, so maybe if you could briefly restate the problem statement, but really then move into what is your research plan? What sort of application do you hope could result from the research that your group is organizing? And ultimately, what are your next steps? We'd really like to see some concrete plans for continuing or starting this collaborative research. And in the spirit of collaborative research, I also want to reiterate that we hope that these breakout groups will continue to work on these drafts, these white papers, after the workshop. In fact, we're hoping that after about 2 weeks' time, we'll have an evolved set of drafts that we can then publish on the website for this event. And that these are not proposals to Microsoft or deliverables for Microsoft. These are public-facing thought pieces that all of the stakeholders who are involved in drafting these hopefully will want to help to implement and potentially invite other people into that implementation and execution process for running this sort of research. So I'll leave it at that. Please go have a little early lunch, perhaps, depending on your time zone, or breakfast, depending on your time zone, or a cocktail, depending on your time zone, if that's what you need to do to get your creative juices flowing. And we will all meet back in about 30 minutes with our breakout groups. And then an hour and a half after that at 1:30 Pacific, or sorry, 1 o'clock Pacific time for our final report back, where the groups will share what they've done, what their plans are, and also hopefully have an opportunity for everyone to provide a little feedback and ask some questions of each of those different breakout group white paper plans. So that's it for me for now. Look forward to hearing what everyone's come up with at the end of the day. Thanks and have a good lunch.